every time we have this session and someone amongst you is there attending, please remind me to record these sessions because for people who are not gonna join, they should have this option of watching the recorded session. Okay, so just always remind me to the first thing that you can just remind me is start recording. Okay. Uh, okay. Now let me share this thing. I have a screen to share. Let's see if you can now see that. Think, yeah. I should have a image here. Let's see what kind of image can we get. Hmm, would be okay. Let's see. Acha, maybe what did you guys learn in the first week? What were the things that were discussed? If anybody completed the lectures for week one, at least we can discuss that. No?
Hello. Yeah. So in the first week, we basically started off with the introduction. This was followed by
Hmm.
some discussions and lecture on the system concepts, and finally we went into the property of the system.
Already, properties are
Yes. Yes.
okay. Sorry, I didn't see who is this person who spoke? Sorry, I couldn't
Uh,
catch
uh,
that.
I'm
Jyotir.
Jyotir.
Jyotir, great. Okay, man. I'll also should shut off my camera now because my internet will also need bandwidth, and you might face some lagging if I keep my camera on always. Okay. I just maybe I'll keep my camera on a little bit longer and then I'll shut it off. Before I formally, so I'm just looking for an image for just to have on the first slide. This will be a common slide every time. Because what I'm gonna do is, in case there are no questions, obviously the first thing that I welcome is that people can upfront randomly ask questions, and that would be the nicest thing. Uh, but the unless it is not there, then I would be what do you say? I would be preparing some slides, maybe some problem questions that we will just solve. Uh, and yeah, I will be primarily be using this uh, presentation format where I will write few things live. I'll just show you how I'll do that. Yeah. So I'll generally this is how I've been doing. I have taken other what do you say? Other other courses, live interaction sessions for other courses also. So this is how do I do it. I have two screens. Um, so actually I'm looking in this screen whenever I'm presenting. So I can just now type things. Let's say P equals to RT, something of that sort, right? So I can do it with this two screen thing. I was just looking for an image, just paste anything for uh, right now. But maybe this thing. This is a nice plot. This is a nice plot to represent what thermodynamics is all about. And can one also answer what should one expect from this course? Like, why did you guys join? Because this is arguably a fundamental course, right? It's arguably a fundamental course. Why would someone join? Are you guys looking for what do you say, fundamental stuff, or is there some other reason as well? Because generally this is a very core course. Nothing very fancy that is gonna happen in majority of the sessions. So yeah. Okay. Let me formally. Okay, there are still people trying to join. Anyways, right. So at any point of time, you can feel free to stop me and discuss things. If you are not raising a point or anything, mute yourself so that others can be what do you say? Can hear me properly, right? Okay. So Uh, welcome all. This is this first session, live interaction session for this course on it's aerospace course, Engineering Thermodynamics, offered by Professor DP Mishra from IIT Kanpur. I will mention that. Is it right? He's from IIT Kanpur, right? Aerospace department, I feel. Uh, hmm. And I will be the TA. There are going to be there are going to be two TAs. uh, One of the TA is going to think check your assignments and all those things, and I will be the live interaction teaching assistant. You can always reach me out and all those things. So I'll just formally introduce myself. I'm a PhD student at Indian Institute of Science, Bangalore. I am from Agra, and I did my bachelor's in 2020 from IIT Ropar. So a Chandigarh University student would know where IIT Ropar is. Uh, and then I briefly worked in HPCL, and then I joined um uh, my PhD program at ISC. A bit of update on this slide. I'm no more in my. I'm not finishing my fifth year. I'm already in my fifth year. I'm not finishing my fourth year. I'm already in my fifth year. So I'm a fifth year student. Oh, let me correct that. And my department is Department of Mechanical Engineering. You can have my contact details. This website is also old. Anyways, does not matter. The more important thing is email. If you would like to ever reach me out, you can reach me out with this email. Um, okay. So now let's get started, right? Okay. So ideally, I am supposed to. I have a. Uh, so this is where I need your input, right? And this is important because that will define how we are going to have these sessions, how we are going to conduct these sessions throughout. We are going to have 12 weeks of this is a 12-week course, right? So we are going to have 12 interaction sessions for every week. And today, our discussion is important because that will finally decide how are we going to conduct these sessions. So that is why I was asking. So at this point of time, I'll just shut off my camera. So I was asking, uh, what were your expectations from this session series? If anyone has some points, because see, what am I required to do as a teaching assistant? I have a list of uh, assignments. These are largely MCQs, objective questions, and we can just discuss those. Uh, or if you have other questions, or maybe you want to discuss few things, or if you want to discuss some challenging problems or something, we can do that as well. Or if you need some help with uh, uh, some concept or some confusion is there with the lecture videos, we can discuss that also. But that will go, like, I think that is something that will come up eventually once you see that if you have a confusion in those lectures, only then you can actually ask questions and we can do that. But so what do you think? Should I just go ahead and I have a list of questions which would you like me to solve those questions, or do we discuss uh, the or should we first overview the course? Pretty standard core course. It's not the first time this course is being offered. In fact, I think this course has been offered uncountably many times. Uh, so a lot of things are it's a very standard things that want to happen. So that is where I need your input. What are your expectations? That is why I'm uh, again and again asking the same thing. Does anyone have any input to share? No. Okay, fine. So somebody mentioned systems, right? So one thing was systems, and then he
Sir, excuse me.
mentioned, yeah, yeah, go ahead.
Excuse me.
Hmm.
Let me say a few things actually. Though I am a
Mhm.
teacher teaching economics for 15, 16 years, still I have enrolled this course because to hear from Dr. D.P. Mishra. Okay. I know he had been to my place before, long before, and we would like to see whether anything extra, something added things or not. That's why we have joined the course. So this session, I think, if you go on the basic point of view and the basic
Mhm.
question answer, no problem, sir. It will be fine for us.
So
To
you
suit your, please go on solving some. If some issues comes, we will ask. That's it. I think it will be nice.
so basically, so you're suggesting that I should go ahead and solve the problems, is it? Is it that what you're saying?
Yes, sir.
Okay. Okay. But you also mentioned that you were there to hear from DP Mishra, is a professor, right?
We have joined that course for that. We that time we didn't know the virtualization, but still it is going on. Whoever is discussing, there's something to learn only.
Got
No
it, got
problem.
it. Because essentially this course is a rerun course. So he recorded those
So we have
lectures while back. Yeah.
like, refreshing things like that, sir. No, so no issue at all. Please go on with the basic things.
Okay. 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 So somebody mentioned, so just before I go ahead and I would like to first overview the content of every week. This is how I have been conducting these sessions before. Just give me another second. I'll open that list of assignment problems that I have. Okay, so if I think that is where we are going, I'll do that.
I think assignments have been given. I think in the assignment section.
So I have a different set of assignments. If you have any questions from those because I think your due date for that assignment was yesterday, isn't it? Or is it the other way? Is it gonna be later?
February, 4th of February, the last date to submit this assignment.
Couldn't could you please type in what because I think there is a little bit of noise, like I can't hear you properly. It's not clear what you're saying. Sorry for
It is
that.
the assignment. I think is given the due date is the 4th of February.
Okay, so you still have time, right?
Okay, but you said, as you said, sir, you have got some new fresh list of problems. Please discuss them and please give them also to us to practice later on.
Okay, okay. So wait, let me do that. Let me open. Anyone else has anything to add? They can also speak up. That's okay. Up. Mhm. So before I go in and discuss those assignments right away, can we quickly, what do you say, review the week's content so that those questions start making sense. So somebody said, Sir discuss systems, properties of substance, and there is something which I missed. Before systems, he mentioned something else. What did he say? If somebody remembers or he can repeat. He mentioned three things.
Hello. Sorry.
Hmm.
It was initially it was about introduction and the applications of thermodynamics. That's number one.
Okay.
Followed
Okay.
by
Okay.
systems
Intro
and then
plus
purpose. Yes.
application.
Applications.
Okay. Makes. Acha, and what did you essentially? What is the concept of systems? If you would like to like speak a little bit of like, we can quickly go ahead. These are not strong concepts, so we can quickly go over these. Do you have any like? Can you describe the essentially what was being conveyed in this discussion on systems? Because the third part, properties, is very interesting. I feel that I also would like to discuss with you guys. Uh, so yeah. So what all systems do we have? If somebody can mention that.
A
What?
thermodynamic system can be any body or any space upon which we focus on for the study of energy and in discussion.
Okay. Although I was able to pick up some part of what you said, still I was not able to completely understand. You mentioned some body or some. So basically,
Region,
you're saying in some. Mhm.
region in
Maybe
space.
maybe it is better that you just type in what you're saying in chat. That way, everyone can actually read it and it's clear. If that I think that is better. But okay, so it's right. There is an open system. There's a closed system. What else? Is there a third kind of system? There's an isolated system, right? Essentially, is this correct? Is this categorization okay, or is this not the like exhaustive categorization? Have I left anything else?
No, it's right.
Okay. And so this was the essential concept, right? That there are three kind of systems. Open system will have certain conditions. Closed systems is a system which has certain exchanges going on, and then isolated system will have no exchanges, right? That is what it is about. And the exchanges I mean by like, so what are exchanges? Exchanges are going to be in form of. Can you tell me what in form of what? Mass and energy, I think, right? Correct. So open system will have mass exchange. Uh, so let me just quickly write this. Mass and energy exchange. Closed system will be just just energy exchange. And then isolated is no exchange, right?
Yes.
Right. So this is it, right? This is it. This sums up the systems thing. Now, what did you learn in the properties part of it? Let's get your narrative out here. Like what essentially were you what did sir what was the narration of this concept in the video lectures? What did he say? If you could sum it up in two lines or one line, then I think he wouldn't have completed it, right? This properties would go on for I think another half a week. Let's see. Properties.
Yes, yes.
Hmm. Huh? Oh, somebody has, I think there is a chat, right? So isolates mass. Okay, people are typing in, right? Oh, I was not able to see this. Sorry, what I'll do is and can I do with this chat? People are typing. So that is okay. That is good. So I keep seeing this. And I'm recording as well, right? This works best for me. There are a lot of people typing. Let's wait for the point functions. Oh, great. Nice. Nice. This is what I wanted to discuss with you guys. Let's discuss these things. I think at this week there are no. So see, I'll tell you what questions there are. Then there will be no motivation to discuss those problems. I'll show you what questions I have. So the week one course is which of the following properties an intensive property? Okay. So we talk about wait. So essentially, there's a question on intensive properties. Then and also definite value at a particular state. Right. So Prashant, what do you mean by definite value at a particular? Okay, so he means that at a particular state, this value will have a single value. It will have a single value. Is it definite? Would you say you mean single value? What do you mean by definite? So one question is about intensive properties. Then which of the following describes a control mass? Okay, so this terminology of control mass. Control mass, control volume, and what else? Isolated, I think. Let's see the chat. People are typing. I'm just waiting. Then there is, yeah, isolated system. Which of the following pair goes from point and path function? So essentially, point versus path function is something that has been already discussed. This is like the primary thing, point versus path function. What I'll do is, uh, I'll give you a nice flavor. Probably you might not have heard this version of thermodynamics. Okay, so probably this is not a original version of thermodynamics, uh, but I feel this is what it is. So I'll write this down. The first law. Let's see how do you like this statement. Okay, the first law of thermodynamics. Define energy as an entropy. Sorry, energy as a state function, as a state function. The second law of thermodynamics defines entropy as a state function, or you could say point function or anything of that sort. How do you like this? Is this digestible? Is this nothing new? Is this something that you have heard before, or is this an interesting way to look at the two laws? So meanwhile, people have said and also definite value at a particular state, I think is a single value, sir, like pressure, temperature, and density. So basically what he means is point functions are at a given state, they'll have a single value. Okay, we'll talk about that. Just can you give me 2 minutes of break? I'll just quickly come. Okay, I'll just go and use washroom and I'll come back. Meanwhile, Akshay can keep on typing. I'll just come back and Yeah, so I'm back. Let's see if people are here or not. Yeah, okay, fine. Checked. So the expression for the state functions are exact differentials. Okay. This is what I wanted. For example, integral of PdV plus integral of VdP equals to integral of dPV, which is a definite integral. Okay. So integral PdV plus integral VdP is a property of the system. Okay. But path functions like integral PDV cannot be regarded as a definite integral. Very nice, Akshay. Very interesting. I would have gone to discuss these two bolded statements, but I liked his comment so much that I would go ahead and discuss his statement. It's very interesting that these see this is what I wanted, so that we have some discussion, right? We need some discussion thing. So first of all, questions to Akshay. First of all, what are exact differentials? Okay. So he kind of explains that. He says that integral uh, PdV plus integral VdP is integral dPV. Is that what he says, right? Let's see what it says. But path, no. So integral PDV is a property, so which is see interesting. No. Okay. One thing is that now third he says, but path functions can't be definite integral. So the third term he uses is definite integral. See, this is where we will loosely say things, and he's not wrong or anything, but it's not precise or exact, right? But I understand Akshay is understands the concept, but let's pick point his statements and uh, talk about the integrities of point functions. That is how we'll go. Okay, so one thing is definite integrals. Now the problem with this statement, the statement is largely true, but then he fails towards the end. He says, but path functions like integral PDV can't be regarded as definite integrals. See, definite integrals, guys, tell me, what is a definite integral and what is an indefinite integral? Does it have to do anything with what do you say with the exact differentials? So my question is, does exact differential or does definite integral has anything to do with exact differential? So my problem, which I'm fabricating, like just to build up our conversation, only for that purpose. Otherwise, your comment on the chat is a very good comment. So just to build up an unnecessary issue with your comment, uh, the see in your attempt to explain exact differentials, you went ahead to say something about VDP and PDP, and finally said that path functions like integral PDV can't be regarded as definite integrals. When you're defining or when you're explaining path point functions, or say path functions or exact differentials, where does definite integral come from? So sorry, sir, I meant to say exact differentials. So now he's saying, okay, so let's say definite integral is out of the picture already, right? He says so that that thing is out of the picture. But so he says, but integral VDP is not an exact differential, is not an exact differential. Kind of correct. Kind of correct. So essentially what he means is that PdV is not the it's not a differential of something, right? It's not, it's PdV, right? You can't integrate it directly. It's not like dPV. I feel that that is what he means. But the problem with this approach of explaining path functions and point functions is that we have not developed the maths that we are trying to use to explain a thermodynamic concepts. I agree that you would say that exact differentials and other things have been taught to us in high school or undergrad maths, but that does not help. Like, does that? So essentially, if I take the words of Akshay, he's essentially saying is any exact differential is a path point function, which is kind of accurate. What kind of? It's accurate. No kind of is needed in that statement. But does that explain? Well, it also does, right? It explains things, but we need to understand what exact differentials are if we go about this thing. So now you tell me what exact differentials are. Okay, one interesting thing. Tell me what space are these integrals taken in? So, for example, what I mean is integral x square. Let me one thing. X squared dx. Now, which space am I integrating things in? I'm on the real line, right? I'm on the real line. So this is a, what do you say? If I call this as a function of if I call this as a function of x, and this function is I, then I is a function from R to R, right? This R. What is that heavy R? I don't remember. Call this R. Double R. Okay. So a real line, right? But see, I'll tell you the issue with this and this statement. I'm trying to pick point the issue. There is no issue with this statement, but just to play around, just to discuss things. See, when he mentions that exact differential statement, that point functions are an exact differential, you understand that he's talking about a state space, right? He's talking about a state space. Essentially, what he's saying, if I'm interpreting it right, correct me if I'm wrong, Akshay. Okay, he's talking about some space. Essentially, what he's saying is that there is some state S1 and there is another state S2, and I am kind of traversing from one point in this space. Let's say I'm traversing from one point in this space to another point in this space, let's say. And I do this. Uh, right. And I'll also have an arrow here. Not so essentially what he's saying is, so nobody's commenting anymore. Nothing. Some if people want to just talk, they can just quickly talk, right? You can say whatever you want or like just say, okay, just keep writing. Okay. So, anyways, what I was saying is, in order to define a state function, he's already talking about he's already taking the help of a state space where to actually define a state space, he has to know state space. So his definition is kind of a catch 22 kind of a definition where he need states to define another state space. I agree with his statement. His statement is mathematically and very accurate. Not, I don't think there is an issue with his statement. But you see, his definition is kind of insufficient. It's not self-contained or yeah, it's not self-contained at least. No issues though. Uh, then what else? So now, but I don't think there will be a better definition also. But anyways, uh, he's right though. This is how you will define a state space. But again, this I'll tell you why I'm not very happy with this. I'm okay with this definition, but again, I'm trying to pick on this definition is that this definition generally comes towards the later half of the thermodynamics course, where we actually look at thermodynamic properties from a mathematical point of view. This is that comes later on, but this is essentially what state space. Now, state space can be S1 can be T, temperature. S2 can be P, pressure. You see how I kind of implicitly assumed that this space has to be two-dimensional. Why was not it a one-dimensional space? Why could it not be a, what do you say? Why could it not be um, why could it not be a real line? Just like how it was in this IX application, like IX example, why it could not be a single dimensional space, or why can it be a three-dimensional space? Let's talk about that. What do you think? Or is there any conditions, or are there any situations when the state space actually reduces to a one-dimensional space? What do you think? And Akshay, you can also answer what do you mean by exact differentials? Because we need mathematical definition of exact differentials to actually talk about anything, right? How do you say what an exact differential is? That is also something that is not very clear. Is there a very precise definition of exact differentials? Let's see. Let's see what comes up. So this is something that I would like to do. What are exact differentials? It's the total derivative of some multivariable functions. Okay. Hmm. In multivariate calculus, a differential or differential form is said to be exact, uh, as contrasted with an inexact differential if it is equal to a general differential dq. Got it. So this is the definition, which is okay. Now, so what it essentially we are saying is that there are two state variables already, and any property or any point function will come out as a total differential. If something is a property, if so essentially his definition or this definition of point function goes like this. If some variable v, and it is a function of two state, at least because you need multivariate now, at least because this is a concept of multivariate. If there is only a single variable, then every variable of f of x, see what I mean, if this cannot be defined, this definition should not work. Let me, this chat, he's also typing, so I want to see what he's saying. Yes, sir, I understood like this. An exact differential at a, so this is what he says. I have understood like this. An exact differential at a point is actually the total derivative of a function at that point. I mean, this is this for a multivariable function representing a thermodynamic property. Interesting. So let's just formalize what he's trying to say. Uh, this definition requires you to know at least two state variables, at least two state variables to define or to check if to if a function of these two variables is a, what do you say, is a state function, state variable or not, or state function or not, or point function or not, does not matter. Essentially, let's say there is some v which is a function of s1, state 1 and state 2. This should be a now what are we saying? We are basically saying that if there is a change in dv, um, if there is a change in dv, then this will be um, mm, right. So essentially, let me think how to put this thing in. See, this is the problem. How do you frame this? Any one of you getting where I'm trying to head in, right? Where I'm trying to head. Can we say what a can we have a mathematical definition for this this state function or point function? So what do I write if I have a function of two state variables? Why what is the definition for a two state variable? What is the definition for a point function here? Well, think would make more sense to say that if you move from this point to this point, dv will always so Akshay, at least you understand what I'm trying to say, right? Am I making sense a little bit? Am I confused because of some right reasons? What do I write? Because right, at least you understand what I'm trying to say, or does it not make sense? Okay, so at least he's understanding. So how do you write this? See, the problem is any function of S1 and S2 will be a state function. Do you agree with that? So V has to be a, so any function of S1 and S2 has to be a, what do you say? State function. It cannot be that it's not a state function. But there are quantities which are, what do you say? Um, there are quantities mhm, which cannot be represented as functions of state properties. Okay, um, that is there. Okay, so let's leave this part of it. Hmm. See, I think the more if we go by the conventional way, right, we actually have to contrast this with a path function. We'll have to say that there is some process going on. Okay, so the definition should go like this. Under a process, if a quantity, uh, if a quantity turns out to be turns out to be hmm, or maybe this is a better definition. I think this is okay. Under I don't want to use cycle. So basically, I was thinking of saying this under a cyclic process, a quantity that does not change is a state function. or a point function, right? And that will be every function of two states, right? Just give me a second. Hmm. That is one. This is what I wanted to say. But then actually we need to. Hmm. Okay, let's drop this idea of trying to do a mathematical definition because clearly I'm not able to make some progress here and go back to this thing. This will actually define this is a good example to define state functions. I think this is a good way to define state functions. The first law of thermodynamics defines energy as a state function. What do I mean? Does anyone find this statement strange or new? Can someone type in and say if this is new or if this is obsolete? Makes sense. Nothing new in that. What do you think? No comments, huh? See, I'll tell you. I'll tell you how I wrote this. See, it's very interesting. How the first law, what is the mathematical, what do you say? Statement of first law. First law essentially says that dE is del uh, Q is delta W. So essentially what you see here is that what is this statement essentially saying is that if I move from, what do you say? Say point 1 to point 2 and across this process or across this line I find some function. I calculate some quantity which is, let's say, heat transfer, and then another quantity which is work. uh, when I add these two quantities, it turns out that whatever I get uh, is will have a value irrespective of what path I choose. Essentially, that is what point functions are, right? But you see how I'm kind of saying this rather than saying the first law. I'm kind of saying this. I'm using this equal sign as a definition sign. You're kind of defining in the energy, right? In the first law of thermodynamics, we don't have a definition for law of thermodynamics, but you're kind of saying that energy is this point function or it this state which adds up, which comes about from two path functions. So in some sense, if you think about it, the definition of state function requires us to have an idea of what do you say, path functions. There exist some quantities which are path dependent. And if I think of it from a mathematical point of view, we can't write anything about these things. There will be no integral in terms of x or anything which will not be a state function. So what I'm trying to say is, uh, so as you mentioned, right, integral pdv. So let's talk about integral pdv for time being. Integral pdv will have different values depending on how you go how you go from between two paths, right? Which makes sense. And for that, we need at least two variables because pdv will be a property which will be what, p square by 2 or something. P square will be the property, so we need at least two functions. So that is clear, right? Why we need at least two functions, right? uh, okay, that is one thing. Acha, you tell me this, another thing. Under what conditions will this space reduce to a one-dimensional space? Is that possible? Can this space reduce to a one-dimensional space? People can try to unmute themselves and talk, or yeah, use the chat. What happens during phase change? How many independent state functions do we have then? Anyone? Okay, I'll leave that. Uh, okay, so I'll go back to this second statement also. I guess I hope this whatever I wrote made some sense to you and was a little fascinating, because I find this definition of first this these two statements quite interesting, to be honest. Similarly, we can also draw an analogy with this second law also. Okay. See, second law is gets defined, and this is precisely how you know second law, right? Entropy gets defined in the second law, right? So entropy is ds. Uh, Similar to how like entropy gets defined in the second law, we can also say that energy gets defined in the first law. That is what I wanted to just convey, which is del Q by T. Now, interesting how both properties, both state functions are getting defined with the help of uh, a path function. So that is important. So we should at least in principle have some understanding of a path function to talk about state functions. Okay. Uh, and path functions, I don't think we can. Yeah, those are not conserved quantities. So yeah, we can say that these quantities don't. So first law is energy conservation. Second law is also entropy conservation kind of thing. We can call it that. But well, that second law states that you have to go in a reversible process. So then entropy essentially does not get conserved in reality. It's only in the quasi-steady conditions and reversible conditions that entropy will get conserved. So essentially, we can also say that state functions get conserved. And that is what I meant when I wrote that under a cyclic process, a quantity that does not change is a point function. So you see a point function will remain conserved under a cyclic process. Point function remain conserved during a cyclic process. Acha, one more thing. I talked about the first law and I also talked about the second law. What about, see, third law is something out of our scope, right? Third law talks about entropy of a solid and at 0 Kelvin, what is happening and so on. It is a very interesting law, but essentially we are going to look at engineering thermodynamics, which is the classical thermodynamics, no statistical thermodynamics. So third law is essentially we are not going to even touch. But what about, there is another law which is left to be stated. What is that law? Yeah, zeroth law. And that this is where I kind of, this is my statement, not precise. Okay. This is my statement. I'm adding this. The zeroth law of thermodynamics defines temperature. So essentially how I like to, as a state, not as a state function, but defines temperature. If I remove this state function, yeah, so at least this is correct. Now this statement is not wrong. Actually, zeroth law is used to define state function, this temperature, right? So this way, this is a quite nice, clean, and very fascinating picture to thermodynamics. And I wanted to just share it with you. This is one thing. And I'll tell you the toughest concept to actually grasp uh, among these three laws is the zeroth law, because zeroth law, when the time, the zeroth law was stated, let's do that exercise. Let's see when these three laws were stated. Okay. Meanwhile, Jyotir is typing. I'll keep a watch here on the second screen, Jyotir. You keep you type. I'll read it. Meanwhile, let's when were the three laws of thermo discovered? Not discovered, stated. Let's find out. This is quite interesting. So first law got stated or formulated around 1850, 60. Entropy work formal was in 1860. You see how this is a little later. The third law got stated in 1906 and 1912. Okay. So this is the third law, and the zeroth law gets defined even after that. So that is also quite interesting. Zeroth law is the very fundamental thing, and it you might not be able to understand, but people have spent PhDs and their doctoral degrees, like these Carnot and these all classical scientists, physicists, and uh, Clausius, and then Kelvin, and then Carnot. All these guys have. This is what they were working out. Okay, just like how we are. Uh, this was the AI of that time. Okay, to be honest, think about how steam engine revolutionized the world at some so just like how AI is today, we should actually appreciate the fact that at some point of time steam engines were the AI of that time. So a lot of people are doing this research on thermodynamics. Definitely this has the time the time for thermodynamics has passed, and we are way past the peak of thermodynamics and other things. These things are done and dusted now, but still very relevant and very, especially very important. Very important what you say when we have to apply things, especially thermal engineering is nothing without thermodynamics. But still, if you talk about from a like from a what do you say from a era of eras in terms of eras, you'll see that um, there was an era of thermodynamics or first law and second law. But important thing is that the zeroth law gets defined the last. Okay, that is important. I'll just read what Akshay said. So when two systems are in thermal equilibrium with a third system, then the first two systems are in thermal equilibrium with each other. Right. Correct. That's the correct statement. But if you think about it, um, actually towards the middle of the course, you will study you'll go through the chapter on entropy. That chapter will talk about the absolute temperature scale. Okay, and I'll tell you how that temperature scale gets defined very weirdly. Okay, uh, that temperature scale actually relies on Carnot efficiencies. TH by TL is I don't remember the exact statement, so let uh, to avoid the risk of being incorrect, let me open Senjel and Ghazal to show you where what am I talking about. I don't remember how that's stated. I know that TH by TL is QH by QL, but still, what is the first about? Let's talk about that also. The reason I'm talking about this is that this is kind of related to zeroth law also. Okay, where would I find that? It will be in the fifth chapter, I think. No, sixth chapter. Somewhere here. Let's see. Yeah, see the thermodynamic temperature scale. And now you will think this is equivalent to the temperature scale we talk about. No, it is not. There's a reason why the Kelvin scale, see the Kelvin scale is the thermodynamic temperature scale. And it's quite difficult to understand what do I mean because I'm not explaining you that well. Why a normal temperature scale is different from a thermodynamic temperature scale. Uh, and I also would have to read on that to actually talk about it. But I'll tell you that temperature is a tricky thing to grasp. Okay, it's not very simple. That is why it has taken so much time for it to get stated. Oh, this thing I don't know, man. Is it available online? I don't think so, right? Don't know. At least I don't have an access to it, so I can't help you there. Maybe you can reach out to professor and ask him or the NAPTEL team. Not sure if I don't have it. Okay, that is one thing. Anyways, uh, okay, and essentially this zeroth law is very important from a point of view that you have to mathematically state it. See, we are dealing very on a very largely hand wavy ways, right? We are talking about some things and physics of it. What is the physical meaning of temperature? What is the physical meaning of energy? But these things have to be mathematical also to get formulated, right? So the zeroth law was about the mathematics of temperature. Anyways, so this is what the zeroth law was about. These are the three things that I wanted to share. What else? What else? Let me look at let's discuss these questions. So I'll ask you the question and you answer this. Okay, let's do this question and answer thing also. Whatever questions I have, let's do that. Hmm. So the first question is tell me what is okay, so we talk about the intensive. So there are amongst density, temperature, pressure, and momentum, which is not an intensive property, which is an extensive property. Answer is momentum, because momentum is directly proportional to the size of the system, okay, or the mass inside it. That is one thing. Then, as I mentioned, which of the following best describes a control volume, control mass in isolated system? So a piston cylinder system is a what kind of a system? A piston cylinder system. Is it a control mass? Is it a control volume, or is it an isolated system? I'm not seeing a chat. I should do that. Um, so piston cylinder has to be a closed system. Uh, then a, so piston cylinder has to be a closed system. Then what about a turbine? What is a turbine? Is it a control mass? Is it a control volume? Or is it an isolated system? So turbine is a control volume. Okay. And then thermoflask. Again, these are very like that is why I didn't want to discuss these things. Very straightforward. Thermoflask is isolated. Then which of the following pair has best represents point and path function respectively? Come on, let's not do these things. Continuum mechanical concept is relevant for which of the following cases? Okay. Did sir discuss continuum mechanics? Not continuum mechanics, the continuum hypothesis. It should be there in this book on continuum thing. See, that is where I'll tell you continuum hypothesis is very important. I'll tell you. It actually is the foundation for anything to talk about from a classical thermodynamics point of view. You need the continuum hypothesis. Like, this is indeed very important to discuss. Yeah. Okay. It's actually better given in this book. I'll open that book. Frankenbite. Let me open it. Right. See, I'll tell you one thing. Let's talk about density as a property, okay? What do you think in homogeneous mixture, density is a state variable? Density changes, right? With the location wherever you are measuring, density will change, right? And if I go to a very small volume, on the orders of let's say angstroms, it is possible that I am in the vacuum of the vast space that atoms do not, or yeah, atoms. Let's say in a gaseous mixture, I'm not enclosing any atom. So what will happen to the density? I'll show you. So as you go to a very low scale, right? These things start making no sense. Density, temperature, uh, then what else? Pressure also don't make sense at very microscopic scales. Okay, and you'll see that there is a large variations in if you start measuring this quantity. So of a small volume and whatever mass is inside that enclosed volume. So you'll see large variations, but at some scales, this value starts to saturate. Okay, so we are going to only deal with those systems which are at least as big as this scale. We are not going to deal with microscopic systems and what do you say, nano scale systems, because there these definitions starts to fail. We're not going to go into quantums and other things. So these properties will make more sense there because the effects of individual atoms and the statistical effects dies down at large scales. Okay, indeed, I have another. Let's leave that. I'll maybe discuss that part later. Um, or should I just go ahead and discuss that? Maybe that is also an interesting part. Let's do that also. Indeed, there is a very interesting discussion in one of these books on this continuum as an important aspect. Okay, we discuss this with you. Where is that book? If you guys have any questions or comments, you can just keep like chat reply on the thing. I don't know. The first week is going to be a little slow there because it's not. We don't have any much to discuss, at least numerically or anything, right? Well, just one thing. Yeah. So what I mean is, let's say we're kind of calculating velocities. I think this is so basically what we're doing here is uh, so let's read this part or what? Okay, let's quickly read this thing, right? Microscopic measurements are not only extremely slow on atomic scales, but they're postponed. Okay, so I'm not gonna read this thing. I'm just gonna tell you what essentially the message conveys. Largely I will have to also read this part. I don't remember also, but largely I'll tell you what. See, suppose we go to a very macroscopic scales. What you will notice is that in the space domain, there will be high frequencies. Now, what do I mean by high frequencies? Suppose if I'm at a very small scale, right? Then velocities will change over a very small spatial distance. Okay. And if I inverse that spatial distance, then I'm kind of measuring the frequency domain or inverse of the spatial distance. Let's talk in terms of inverse of spatial distance. If you keep averaging things out, let's say if we are calculating velocities, let's say this is a one-dimensional system. Okay, this is not a two-dimensional systems. And this thing can have there are a lot of atoms, and different atoms can have different velocities. What will you expect at a very low scale? And suppose this is an ideal gas. So we know that assumption, right? No two atoms affect each other, and so on. There is no force or anything, and the velocities are at random, right? So there is a normal distribution of velocities, how the velocities are distributed over different atoms. So at any point of time, in principle, any atom can have any velocity, right? So now with that assumption, if you think of it, if you pick a small window, very atomic scale window, you what you will see is velocities will be varying across uh, large what do you say? Uh, there will be large variations. One atom will have some velocity, let's say 0. Other will have plus 10. Other will have minus 100. So you will see large variations. Now let's say we do averaging. You know what averaging does. Averaging dies the effects of outliers dies down on averaging. So once you average things out, essentially what you see is that your variations starts to get what do you say? Those slopes become smaller. So you don't get very large. Now here the word modes is used. Now, what do they mean by modes? Essentially, they are saying in terms of inverse of spatial distance, you will have large variations or large variations over small distances. But if you average things out, the velocity is not going to change uh, largely if you are averaging things out. Okay. On a large scale, velocity, it's not that the velocity of the entire system is going to be plus 100 and then minus 10 and at some other instant 0. On averaging things out, the velocity of a large, let's say large pressure vessel will largely be 0, right? That is what I mean. But if you go to a very small scale, uh, velocities can be erratic and so on. So that is what. So essentially, when we say state functions, at some point of time we are actually averaging things out. That is an important thing to note. We average things out to actually define state functions. So state functions is a what do you say, is a culmination of some averaging going on. Okay. And the continuum mechanics comes in here, that our system has well-defined properties. We are not going into these scales, so there is variation in densities and so on. If I pick at some point, uh, if I select a point in space, that at that point properties are well defined. It's not like this. So if we are assuming even our point has this resolution, the resolution is so low that it does not go into this region. If I'm selecting a point in space, that point in space encompasses, let's say, this much of volume. So so this much of volume is 10 to the power minus 9 meter cube, which is 10 to the power minus 3 meters. So 1 micron. So we are kind of assuming that above 1 micron, or if I am selecting my point in space, that point is let's say 2 microns in width. So it's not that we have zero width. Even if we consider, we say point, but essentially our point is not that resolved. Okay. So remember that this is much required to actually treat thermodynamics from an engineering point of view. Otherwise, the definitions of density, temperature stops making sense, because in a given point of time, it, you might not have an atom there. It might be vacuum, right? So the definition of pressure does not make sense. Pressure comes when you average force, when you average force on some wall, right? Pressure otherwise don't make sense if you think it from a atomic point of view, when there are a lot of ideal gas models and all those things. Pressure will not make sense. Pressure will only make sense when you average force on a wall. Or temperature will comes from averaging the uh, kinetic energy in a system. So those things will come in. Then what else? That physical, what do you say? That physical equivalence is not available for entropy. Let me say that upfront. So you might say that entropy means randomness and so on, but that is not very precise. Okay. Uh, so it's not. There is no physical. There's no physical way to understand entropy. Okay. That is another important thing. So we have physical construct to understand pressure, temperature, specific volume density, but not entropy. Entropy is a little tricky. Okay, so this intensive thing is done. I don't know what to discuss the man. Come on. So these things. Then there is a manometer question. Let's do this. What is this question? Let's see. Hmm. Let's discuss this question. Or in a new slide. So the question is. So the question is, the water in the tank Wait. Why did this image go? So the water in the tank is pressurized by air, and the pressure is measured by a multi-fluid manometer. Determine the gauge pressure of the tank if H1 is this, H2 is this, and H3 is 0.46. Take the densities of water, oil, mercury to be 100,000. Okay, let's do this question then, if that is the thing. The question is, question says that H1 would, okay, or maybe I can also wait for you guys to solve this. This is a very simple problem, so let's see. And again, this is not a thermodynamic problem. This is a fluid mechanics problem, I feel. But anyways, 0.46. And then you have density of water available with you is 1000 kg per meter cube. Then you have density of oil, which is how much? 850 kg per meter cube. And then we have finally mercury, which is how much? 13,600 kg per meter cube. Okay, now you need to tell me the pressure of the air inside this tank. That is the gauge pressure, okay? So not the absolute pressure, but the gauge pressure. Basically, what I'm asking is P at air minus P naught or P atmosphere. That's okay. So P naught is P2, I think, right? P2 is P naught. So I'm just trying to find P air minus P2. So can you guys do this thing? Let me just if you guys can do this question, just type in the chat that I am kind of solving this question right now. I need 2 minutes or something. Just type in the time I'm doing it on it. Oh, and you cannot see the figure. So I'll remove this. Meanwhile, let me see. Okay, so this is straightforward. So let's write this thing. See, P2, let's move from, so I'm right now here. So I'm saying this is P2 and I need to find this quantity. Okay. So let's move towards this direction. So what we'll do is we'll go up this manometer to 1 to see what this thing is. So essentially you're trying to find P1 minus P2 based on this drawing. So P1, or I'll start with P2, I'll go down. So we go down till till this point, okay? Till this point. So the pressure at this point will be P2 minus rho GH, right? Rho But what density? The fluid is mercury, so rho g, and this will be rho plus. Okay, pressure increases in the direction of. And one more thing, mercury has a symbol of Hg only, no? Okay, got confused. Okay, fine. Got confused. So then rho g H3 into G. Now from whatever this Pascal's law or whatever that law is, we know that these two pressures are going to be same. So now we move up this direction and go here. So this density, this pressure will be minus rho, what is it, whatever this is, oil H2G, right? And again, using the same, whatever that law is, we are here. So this pressure and this pressure are same. So now I go down here. Okay. And then come back up here. So this thing cancels out. Okay, so I don't need to go down here. This is where I am right now. Is this correct? Am I making sense? Am I going, and my procedure is okay, right? And so now if I want to go up towards the air, I just simply minus this rho water out also. So rho water H1G. And this will be what? P1. I need to find P1 minus P2. Yeah, so this is the formula for it. We'll put in the numbers and we'll get the value. Not going to do that. What else is there? Okay. Let's do this question. Pressure cooker. Okay, so I'll have to, for this, I will have to. So let's read this question. I just. Probably tell me if these questions are there in your slides also, or like this times also you have the same questions. Tell me that, okay? Right. So what does it say? So pressure cooker cooks a lot faster than an ordinary pan by maintaining a higher pressure and temperature inside. The lid of a pressure cooker is well sealed and steam can escape only through an opening in the middle of the lid, a separate metal piece, the petcock. Sit to the top of the opening and prevent steam from escaping until the pressure force overcomes the weight of the petcock. The periodic escape of steam in this manner prevents any potential dangerous pressure buildup and keeps the pressure inside at a constant value. Determine the mass of petcock of the pressure cooker whose operation pressure is 100 kilopascals, 100 kilopascal gauge, and has an opening cross section of 4 what 4 mm square, I think. Assume atmospheric pressure to be 101 kilopascals. Pretty okay question, not very tough. Let's see what can we do. What can we say? What I'm gonna do is I'm gonna build a force body diagram of this petcock and just finish it off. Okay. So there are no forces in the y direction. So there are no forces in the x direction. There is only forces in the y direction. This is the petcock. The cross section is given to us to be 4. So this is A. I know that there is a pressure on P naught. And then there is a pressure which is P inside, or let's say P whatever. side. And now I need to find, so when this pressure cooker will, or this petcock will open up, when this difference in pressure into area is equal to mass of this petcock into G, right? So then essentially what you have is I minus P infinity for P naught is mg. Now this is given to us to be 100 kilopascals. And this has to be into area also, important. So 100 kilopascals, which is 10 to the power 5 into times what? Area, 4 mm square. So 4 divided by into 10 to the power minus 6 meter cube, sorry, meter square. Yeah, and G is 9.8. So you divide by 9.8 to get what? One thing is, let me cancel these things out. So this becomes, let me treat it as 10 only. So then this becomes 10 to the power minus 2 kgs. Okay. And now I want to get it in grams, which is like 40 kgs, 40 grams, 40 grams. So this will come out to be 40 grams. Okay. What else? So these are pretty standard questions. I don't know. Is there a point to do these things or not? Pretty standard things. See, how much time do we have? I think we can close here. What do you think? Should we close here? Because these questions are not that great, to be honest. Simple, like 1 mark questions. Anyways, so what I'll do is I'll stop here, okay, for the first class. Let's see what we have to discuss in the next few classes, okay? So let's do that instead. Okay, that is going to be interesting. So how does this course go? First few weeks, I want to have a course overview, which would be somewhere here, I think. Right. Yeah, this is the interesting part. Okay. Uh, and this is actually quite interesting. So we'll do this. Slightly touch statistical picture of thermodynamics. Then phase change, as I was talking about, in this regime, that state space reduces to a one-dimensional space. Okay. And the reason that we were dealing until now, we have been dealing with what do you say, a two-dimensional space, not three-dimensional or four-dimensional, is because of Gibbs phase rule. Okay. So mind that. Yeah, right. Mind that. So it's always so if we have three states, pressure, density, and temperature, we know that pressure will be a function of other two state variables. So we have a degree of freedom of only two. We can independently vary only two states. Okay, so that comes from Gibbs phase rule. Uh, if I have something to add on those lines, mm, I'll check and I'll let you know next time. Okay. And then yeah, so this is pretty standard way to go. So next time, let's see how these things, we will discuss a few things. Please collect questions if you have. because that accelerates our discussion. Otherwise, I'm gonna be talking as a monologue, which personally there is no point to. Okay, so there's no reason that's not helping you or me. So it's better that if you have any questions or something that you would like to discuss, that would actually help our this series to go. Okay, so maybe we'll stop now and meet next week. Anything, anyone? Please, now is the time, or we can end the session. Yeah. So thank you guys. Let's meet next time. No need to call me sir. I'm maybe I'll be like small like younger than few of us. So please don't call me sir or anything. You can call me by my name. Okay. Thank you everyone. Okay. Nice to. Please be there on next time. We'll discuss some interesting problems or something. Okay.